for Thursday, October 1st, 2020. So we started with the opener, which had to do with a combustion analysis. This one's just involves a hydrocarbon fuel. Let's get our pen going here. So a hydrocarbon fuel right here. So instead of having oxygen in it, all it has is carbon and hydrogen. Okay. So here's the solution for this problem. I changed the problem a little bit and made it an excess instead of having an actual number for the oxygen, so that you wouldn't have to check whether there was excess oxygen or not. And so, in order to find the empirical formula for the hydrocarbon, we need to find the moles of carbon and we need to find the moles of hydrogen so that we can write a mole ratio into the formula. So here we're taking 23.118 grams of carbon dioxide and converting that into moles of carbon. First, we change it to moles of CO2 using the molar mass, and we use the mole ratio in the formula to get to moles of carbon, and we get moles of C here. We do the same thing with the H2O and convert that to hydrogen, but remember in this case, there are 2 moles of hydrogen for every 1 mole of H2O. So because of that, we just make sure that you remember this factor of 2 and look at your formulas always when you're converting into elements in a particular compound. So then we get these moles here. We divide by the smaller number of moles. This one is the smaller one. Okay, so that will give us 1 mole of H and 1 mole of C. So our empirical formula is CH. So a recap of what happened in the previous class. So the previous class learned how to write electron configurations, talked about effective nuclear charge and the screening or the shielding effect. We talked about Coulomb's law and how the nuclear charge was used to determine the strength of attraction and the amount of energy required to remove electrons from an atom or an ion. And we learned how to interpret PES data and explain the peak positions for different elements. So today we'll cover how to use periodic trends and how to explain the trends using our knowledge of effective nuclear charge, the shielding effect, and Coulomb's law. And we will not get to this. That's for 10. If you watch the 10.2 video, I do this very briefly at the end. And so this unit is really to set us up to learn about how atoms bond. And so one of the central ideas in chemistry that I think kind of underlies the whole, well, actually the whole sort of, the world and the universe is kind of the fact that the structure and bonding of matter gives rise to physical and chemical properties. Okay, so here, structure of matter, meaning atomic structure, okay, will give rise to certain properties of the elements, and then which in turn react to form compounds, and this will provide the function of the material. These properties of these compounds and elements give us function and how we use the substance in the world. So here's our essential question for 1.7, for topic 1.7. We want to explain the periodic patterns in the properties of elements on the periodic table based on concepts of electron configuration, which we learned the previous day, the shell model. The shell model is the same as the Bohr model. Okay, nuclear charge, the shielding effect, and Coulomb's law. All right, so we're going to talk a little bit more about effective nuclear charge. We kind of went over a general idea of it being kind of the charge felt or experienced by the valence electrons or electrons, particular electrons in the atom. Here we're going to talk about the valence electron in particular and think about what the effective nuclear charge would be for a valence electron in these various atoms. So we kind of just talked about this generally, but now we're going to use a formula for the effective nuclear charge. Z effective, okay, so Z effective is the same as effective nuclear charge. Okay, so that's what I mean by Z effective. So we can calculate Z effective by taking the number of protons in the nucleus and subtracting off the number of core electrons. So for example, if we look at potassium right here, okay, potassium, Z effective would be the number of protons, which is 19, minus the number of core electrons. That would be these electrons right here. These are the core electrons. Okay, this one electron here, this is a valence electron. I'll just abbreviate that as VAL. So here, Z effective is 19 minus 18. This gives us an effective nuclear charge of about 1. Okay, so let's look at sodium here. Sodium has a charge of plus 11 in the nucleus. Okay, number of protons is 11, minus the number of core electrons. Again, these are the core. And this one electron in the third shell, this is a valence electron. Okay, so Z effective is 11 minus 10, which is 1. Could it be a coincidence that Z effective is the same for sodium and potassium? Well, if we look here, they're in the same group, okay? They all have, remember, in group 1, we have 1 valence electron in group 1. Okay, so in group 1, we have 1 valence electron, and so that core, okay, is always going to shield the nucleus, and then we'll have 1 valence electron. So we can see that Z effective is approximately equal to the number of valence electrons in that group. All right, so if we take a look at lithium now, okay, lithium's Z effective, let's see if it follows the same pattern as sodium and potassium. We have 3 protons minus the core electrons. Okay, so subtract this off, we get 1 again. 1 valence electron, and Z effective is 1. So we can see that Z effective, the effective nuclear charge for group 1 is going to be 1. Okay, it's staying constant in a group. So in group 2, and I ask a question of whether you know the valence electrons in groups 1, 2, 13 through 18, that will come up a lot. In group 2, we have 2 valence electrons. Guess what the effective nuclear charge is for group 2? Well, here we go. In group 2, okay, let's take a look at calcium here. So calcium, Z effective for calcium is going to be 20 protons minus the core here. Okay, the core is 3 shells that are full. Minus 18 gives us 2. Okay, Z effective is 2. Here's Mg. These are all atoms in group 2. Okay, so for Mg, our Z effective is equal to 12 minus our core. We get 2. Okay, and based on this, you can probably see that Z effective for beryllium is 4 minus 2. It is also 2. So Z effective for group 2 is equal to the number of valence electrons here. Okay, so got 2 valence electrons for group 2. Okay, and Z effective is 2 for the valence electrons in group 2. What do you think it will be for group 13? Well, based on our pattern here, we had +1. We had 1 for the effective nuclear charge for group 1. We had 2 for the effective nuclear charge for group 2. So Z effective, the effective nuclear charge for group 13 is going to be 3. There are 3 valence electrons in group 13. Okay, so this will start explaining why we get some periodic patterns. So for atomic radii, remember atomic radii is the size of an atom, size being defined in different ways, but basically the size. And based on this data, we can see that the atomic radii increase, right? As we go down, we can see that the size increases. I'm going to use AR as an abbreviation for atomic radii. As we go down, we are occupying an additional energy level, an additional shell of electrons in the atom, right? So now the valence electrons in group 1 here, let's use a different color here. So we've got each of these atoms in group 1 have 1 valence electron. Okay, that valence electron is getting further and further from the nucleus. Okay, this is making the atom larger. Okay, and we can see this similar pattern for group 14. Now this is kind of an older notation. Now we use group 14. Okay, so what about going across? Well, now we're seeing that the atoms are getting smaller. Our atomic radius is decreasing. Actually, let me go back for a second. So the atomic radius is increasing. We're adding an extra shell of electrons, right? So even though our nuclear charge is increasing here, our Z effective, remember, is staying about 1, is constant. So our effective nuclear charge is not really changing, okay? But we're adding more electrons, and so it's unable to pull it in even if the nuclear charge is increasing. Okay, so across the atomic radius is going to decrease. As we go across, we are adding electrons into the same energy level. However, we are increasing the number of protons as we go across. Our effective nuclear charge is increasing as we go across, but our electrons are going into the same energy level. So if you watch here, right, for lithium, okay, we've got 1 valence electron. Beryllium, we've got 2. Okay, then when we go to boron, we've got 1, 2, 3. We keep on adding electrons, but they're going into the same energy level. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6 for oxygen. See if I can crowd them all in. Oh, fluorine's going to be a little bit difficult. And then neon has 8. I'm really going to have to crowd those. Okay, so we are adding into the same shell. However, let's look at the effective nuclear charge. What's happening with that? So if we look at the effective nuclear charge, the effective here, okay, let's make a chart for lithium, it's equal to 1. For beryllium, Z effective is 2. For boron, Z effective is going to be, again here, plus 5 minus, okay, the core, it's going to be 3. Here we have 4, 5, 6, 7, okay, and then we have a Z effective of, well, this is a weird case, right? Z effective is going to be 8. I guess it's not really weird, but it's quite large. Okay, so here now our Z effective, right, is increasing as we go across. However, we're adding electrons to the same outer shell. So the nucleus is pulling in those electrons and the size is decreasing. Right? So higher charge, looking at Coulomb's law, higher positive charge in the nucleus, okay, pulls in the valence electron, which has the same charge, and the distance is getting smaller between the nucleus and the valence electron. So this is going up, this is going down, the force goes up. Okay, the attractive force is going up. All right, so a couple questions. Based on atomic radii, which of the following molecules would you expect to have the shortest bonds? All right, so if we take a look here, we have F. Let's outline those. We have F, C, L, and B, R right here. These are our 3 elements that we're looking at. And so if we take a look here at these elements, we can see that as we go down, our atomic radius is increasing because we're adding that extra shell of electrons. All right, so as the atomic radius increases, here's F2. Okay, then we have slightly larger, this is going to be Cl2. And then larger still, oh, sorry, that atom is getting very oblong. Let's try to make that atom a little bit neater. Make both of these atoms a little neater. Okay, so Cl looks like this, Cl2, and then Br, again, adding an extra shell of electrons. The atom increases in size even more, and we have Br2. Okay, so our bond length is measured from the center, the nuclei to nuclei here. That's going to be our bond length. We can see that because the size of the atoms is increasing, the bond length is also increasing. So the molecule with the shortest bond would be F2. Okay. Oh, we have a blank page here. Okay, next. It says, which of the following is expected to be the correct order of atomic radius from smallest to largest? Select all that are correct. Okay, so there could be more than one. Let's look at the number 1. We have MgAlAr. As we go across, here's our general trend, atomic radius decreases. Okay, so as we go across, it decreases. Okay, so we are going to look at Mg. Mg would be the largest, and this would be the smallest. So that is not a correct choice. Okay, looking at the green, again, atomic radius decreases going that way, going to the right. Okay, and we have, so going from S to Na, the atomic radius would be increasing, and that's what we want, right? So we have the smallest here to the largest. That would be smallest to largest, so 2 is a correct choice. Okay, let's look at number 3. So now we're looking at the 3 blue elements in group 1. Going down, atomic radius increases. So if atomic radius is increasing, that means that lithium is the smallest and rubidium is the largest. Okay, so that is not a correct choice. Okay, phosphorus, arsenic, and antimony. So going down, we're increasing, and we can see that phosphorus would be the smallest, and antimony is the largest. Okay, so 2 and 4 are both correct. They're ordered from smallest to largest. Okay, which has the larger radius? Oh, now we have an atom and its ion. Okay, so let's see if we draw an aluminum atom. What do we have? We have a nucleus that's plus 13, 13 protons. Then we have 1s2 here. We have our 2s2, 2p6, and then we have our 3s1, sorry, 3s2, 3p1. Okay, so we have 3 valence electrons in aluminum. All right, so that's our aluminum atom. What about our aluminum ion? This plus 3 means it has lost 3 electrons. Over here, we had a total 13 electrons. Over here, if it loses 3 electrons, it only has 10 electrons. So in the center, the nucleus has a plus 13 nucleus. We have our 1s2 electrons, and then we have our 2s2, 2p6. All right, so guess what? We don't have that outer shell anymore. The valence electrons are gone. Therefore, which one's going to be larger? Well, it's always going to be the one with more electrons. Electrons repel each other because they're all negative. So having more electrons means that the electrons have to spread out a bit and make this aluminum atom larger. Okay, so if you have more electrons but the same nuclear charge, the thing with more electrons has to be larger. Okay, so let's look at a couple more ions. So we want to get the correct ordering from smallest to largest for these ions, and we have an atom here too. Okay, so they're not going to be all the same size. We already talked about the fact that we've got different atoms here, so different nuclear charges. So let's make some Bohr model drawings again. So I'm going to do F minus. Okay, I know that F normally has 9 electrons, but this minus sign means that it's gained 1. So it has 10 electrons. Okay, so in the nucleus, we have a plus 9, 9 protons. Then we have our 1s2 electrons. And then we have our 2s2, 2p6, right? We add that extra electron into the 2p, and that gives us a total of 10 electrons. Okay, so that's F minus. What about neon? Well, neon is just an atom and it has 10 electrons. Okay, so it looks just like fluorine except its nucleus is a plus 10. So it looks exactly the same except that the nucleus is different. All right, now looking at sodium. This is sodium plus, sodium ion. Sodium normally has 11 electrons, okay? But then it loses 1 electron in sodium plus, so minus 1, it has 10 electrons, okay? Just like F minus and neon. So here we have sodium has a nucleus with 11 protons, and then it has its 1s2, 2s2, 2p6 electrons just like before. All right, so which of these is going to be the smallest? Well, we know that the nucleus with the highest nuclear charge, the highest positive charge, will be able to pull in 10 electrons more tightly than a nucleus with a plus 9, right? It just does not have as much positive charge to pull those electrons in. So this sodium plus ion will be the smallest, okay? So that's the smallest. So it has to be either 5 or 6, right? Because we decided that sodium is the smallest. And so then the plus 9 nucleus is going to pull those 10 electrons in the least tightly. Okay, so we know that this is going to be the largest, smallest, and we have largest. Okay, so our largest is over here. Okay, so choice 5 is the correct one. Okay, so here's just a general overview of these atoms and their ions. So you can see that when things lose electrons and become cations, become positive ions, they're always going to be smaller. Okay, and if remember, cations has a T and it looks kind of like a plus. So those are the positive ones. I also think that cats are positive. I like fluffy cats. So that will help you remember that cations are positive, okay? And anions are negative, okay? Anions are negative. So if we take a look here, if we're gaining electrons, they are going to repel each other. That's going to increase the electron repulsion. So anions, negative ions, will always be larger than their parent atom. Okay, the parent atom being the atom that the ion came from. All right, so now we're going to actually look at some trends and talk about why they happen. So as we go down a group, all right, so here's group 1 at the bottom, these red. Okay, that's group 1. So here, let me circle these. These are on group 1. As you can see, there's a general trend of the ionization energy going down. Okay, so ionization energy is decreasing, which means that the electron, okay, we'll say the valence electron, because this is just looking at the first ionization energy, is harder to remove. Oh, sorry, I did it again. Meaning that the valence electron is easier to remove, less force is required. Okay, this means this is due to the valence electrons again going into that outer shell, which is further from the nucleus, right? It adds in an additional shell as we go down a group. Okay, so this is a direct application of Coulomb's law. Distance, right? The farther away you are, the attractive force is going to go down. All right, so as we go across a period from left to right, okay, going this way, let's pick out some elements that are in the same period. So here we go from lithium. The next one is, this is Be, then boron, carbon, nitrogen, oxygen, fluorine. The general trend is that as we go across a period from left to right, our ionization energy is increasing. Okay, meaning that it's harder, meaning harder to remove that valence electron. Okay, that's due to increased proton charge, increased nuclear charge acting on the electrons. Okay, and ever increasing nuclear charge, effective nuclear charge across the periodic table. Again, Coulomb's law, right? If we have more charge, higher charges, we get more attractive force. Okay, so we actually went over these questions in the next class, and I ended up skipping a bunch of these slides, and I go over these on the 10 to October 2nd slides. and talk more about that. And so what we ended with on this day, I also, on the 10-2 slides, I go over this explanation for nitrogen's, for oxygen's ionization energy being actually lower than nitrogen instead of the expected trend. So this is kind of where we ended, and the other material is on the next slides. Just two more properties. Electronegativity, okay, is the tendency for atoms to attract electrons in a bond. So this applies to covalent bonds in general, okay? And we will talk a lot more about that later in Unit 2. So some atoms really love electrons. They will hog and take electrons. They're very greedy for electrons. And other atoms are not so greedy. And so we know that well, we don't know, but our highest electronegativity, fluorine, has the highest electronegativity. Fluorine is extremely greedy, does not ever want to give up electrons. It likes to take electrons and hold on to them. Okay, so it has the highest electronegativity when in a covalent bond. And so the trend is if you go down a group, so again here, if we look at lithium, okay, sodium, potassium in the same group, electronegativity is decreasing. Going across a period, okay, so here's our period trend. Okay, our electronegativity, okay, is going to increase. All right, and we'll talk a lot more about electronegativity in Unit 2 because it really is applicable to bonding and polarity of covalent bonds. So we'll talk a lot more about that when we get to Unit 2. Now, electron affinity, I should have left here a space for the definition. Electron affinity is the energy, okay, that is required or released when an electron is added to a gaseous atom. Okay, so now it's the opposite process of ionization energy. Ionization is when we lose electrons. Electron affinity is when an electron is gained. Affinity is kind of like, you know, do you like it? Does the atom like electrons or does it not like to take electrons? Affinity means how like, you know, how much it wants the electron, how much attachment it has for electrons. So there's no general trends for groups really, not 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 really a pattern so much. But if we look at certain groups, electron affinities, especially if we look at group 17, you can see that the electron affinities are pretty large and negative. Why is that? Well, we know that fluorine has 7 valence electrons, and we'll be talking about Lewis dot diagrams pretty soon. Here's our 7 valence electrons for fluorine. If it gains 1 electron, it looks like neon. It's got 8 electrons. It's got that closed outer shell now, okay? So it is very happy. It will release a bunch of energy when we add an electron to it. So all of the halogens in group 17, very happy to take on electrons, right? The release of energy means that we're lowering the energy of the atom, becoming more stable. So we can see that there's quite a big release of energy. Now, why do we have all positive for the noble gases? Well, guess what? They don't want to take on electrons. They're happy as they are. So, in order to force our noble gases to take an electron, we actually have to put in energy and smush that electron onto them. So so it's got positive energy to do that, and then you can see that in some cases. Oh, look at here. Nitrogen, the electron affinity is greater than 0 again. Nitrogen does not want to take on another electron because, again, if we look at the electron configuration of nitrogen, 2p, if we have to smush another electron in here, we're going to have to pair it up into a half-filled orbital, and we're going to have to create a bunch of repulsion in that orbital. So it's going to require energy to smush that electron in there. All right, so we can look at some other patterns too, but for now, those are kind of some patterns that you should see there, some tendencies, and but there are no real group or period clear patterns to electron affinity. All right, and then we stopped here on 10.1, and so we'll end this segment of periodic trends.